All right, to begin test two material, we're going to turn now to chapter 6 and actually talk about some planets in our planetary astronomy course. That's actually what Astronomy 101 is. Um, Astronomy 102 is stellar astronomy, so it deals more with stars. All right, so anyhow, we're going to talk about Earth. And the reason that we talk about Earth is because it's the planet that we know the best. I mean, obviously, we live on this planet. We've been, you know, investigating this planet for a long, long time. All right, so this is a picture from space. Obviously, if you are not between the sun and the Earth, you're going to see you know a you're going to see a phase of the Earth. This happens from, from this perspective. The Earth is in crescent phase. All right, so that's just that's you'd have to be in a spacecraft obviously, or maybe on the moon or something like that. So let's go over these slides. So the Earth is basically a giant rock, a spherical rock. It's made of different materials, of course, different rocky materials, but it's mostly rock. There's of course water uh, covering two-thirds two-thirds of the well, is it two-thirds? Yeah, I think it's about two-thirds of the planet. Uh, and all right, so anyhow, the Earth is of course spinning on its axis once roughly every 24 hours. It goes around the sun in 365.24 days. Um, and it's so you could actually work out this speed, the speed of the sun. It turns out to be close to 30 kilometers per second, which is roughly 30,000 meters per second. What's really important to us as well is that the Earth basically it acts as though, well, yeah, it acts as though it has a blanket around it. Blankets, believe it or not, are um, part of the greenhouse effect. It's an example of the greenhouse effect. That sounds like a strange thing because with greenhouses we normally think of glass, that the visible light goes through the glass. We'll get more into the greenhouse effect um, in a little bit later in this chapter, but just realize that the Earth would be a whole lot colder if there was not an atmosphere around us. We're also protected by this natural occurring magnetic field that is generated by the interior of the Earth. We'll get a little into that, why that is as well. But what that does for our planet, for example, the Mars, which we're a long time away from talking about Mars, but Mars doesn't have an overall magnetic field, and so that Mars, in fact, has lost most of its atmosphere. We think in the distant past it had a very substantial atmosphere, and now the atmosphere of Mars is um, about 1% the atmosphere that the Earth has. And so the Earth's magnetic field basically deflects charged particles that come from the sun. There's a constant stream of charged particles. We call those charged particles the solar wind, and that protects us enormously. Um, all right, we'll get more into the solar. Well, we'll get into the charged particles colliding with the Earth at the north and south poles. Those, by the way, just since I'm talking about it, they're called the aurora. All right, anyhow, let's get so the Earth, of course, because it's spinning, it is a little bit longer. The distance from the center of the Earth to the equator is a little bit longer than the distance from the equator to either the north or the south pole, right? So it bulges a little bit in the middle because of this spin, and that's because of what's called inertia. objects want to keep going in a straight line, and because the Earth is spinning, the Earth the matter that makes up the Earth piles up along the equator, a little bit more than like at the poles. All right, so that actually has a technical name. You think of the Earth as a sphere, but it's actually what's called an oblate spheroid. That's the technical name for it. I mean, we will definitely treat the Earth as though it were a sphere, because as you can see, it almost is, right? It almost is a sphere. It's only slightly different. All right. Anyhow, so now if we look at the rocks on the Earth, all right, the rocks on the Earth are made of, if you look on the periodic table and you say, all right, well, what are the rocks made of that we can find on the periodic table? So if we break the rocks down into their elements, right, that's what makes up the periodic table. It turns out that rocks are mostly oxygen, right? I'm talking about the solid material. Obviously, the oxygen we normally think of, we're talking about the atmosphere. The 21% of our atmosphere that is breathable oxygen, O2 molecules. But that in rocks, the oxygen, and usually the oxygen and the silicon are bonded together, and they form what are called silicates. Most of the rocks on Earth, not all, mind you, but most of the rocks, pick up the average rock on the, you're walking along a path or something like that, out, away from a city or something like that, and you pick up the average rock, you're more than likely going to find a silicate. Of course, there's other types of rocks, like granite and things like that. But this is not a study in geology. Not exactly. I mean, it's a little bit of geology. So anyhow, so rocks are a little more than 45% oxygen, about a little more than 27% silicon, and then it starts to go down dramatically. Aluminum is only about 8%. Iron, which we do find on the surface of the Earth, which is kind of a strange thing. We'll get there's a reason that there's some iron has to do with the moon, the formation of the moon, actually. So the iron, there's about 6.2%. Calcium, as you can see, a little more than 4.5%, and then magnesium, and then it just keeps going down after that. So silicates, as it says, are basically quartz material. Like sand, for example, is made of silicates. All right, let's move on from that. All right, so the density. All right, so there's this concept, a very important concept in astronomy called density. And we use this, you can see this Greek letter. This is actually a Greek letter. I know it looks like a P, but it's actually called rho, R-H-O. All right, so the Greek letter rho is the symbol, not just in astronomy and physics, but chemistry also uses the Greek letter rho to symbolize density. All right, so rho is the mass of something divided by the volume of something. All right, and so they're actually showing you the volume equation for the Earth, right? Since the Earth is a sphere, as not exactly, but almost a sphere. All spherical objects have a volume of 4/3 times pi times whatever the radius is to the third power. All right, so this is our first formula in chapter 6. There are not a lot of new formulas in chapter 6, but this is one of them. At any rate, mass is normally measured in grams for our purposes, and the radius will normally be measured in centimeters. Like planets, normally you get the radius in kilometers, and you need to change that to centimeters. And let me just state right now, in 1 kilometer, there are 10 to the 5th power of centimeters. So that's a conversion you can use. The reason that we measure stuff in grams per cubic centimeter, and by the way, in hospital settings, these are called, grams per cc. You'll often see cc's. For some reason, they don't like to say centimeters raised to the 3rd power. But a cc is a cubic centimeter. That's exactly what this means, right? It's the same thing as centimeters to the 3rd power, a cubic centimeter. All right, but for some reason, hospitals like to say cc's instead of centimeters to the 3rd power. And at any rate, and one other thing, 1 milliliter of fresh water is 1 cc, right? So a milliliter of, not salt water, because salt water is a little bit more dense, turns out to be 1 cc. So I'm talking about volume here. Now, notice it says water has a density of 1 gram per cubic centimeter, right? So in that, we're talking about fresh water. So just pure H2O, right? No salt, nothing else. The salt water is a little bit more dense. All right, so the rocks that you find on Earth, that we were just talking about, like the average rock made of quartz, has a density of about 3. It's actually closer to 3.3 grams per cubic centimeter. And the density of iron, so if you had a piece of pure iron, its density is it's really close to 8 grams per cubic centimeter. It's actually closer to 7.9 to be more exact. But the average density of the Earth is 5.5. And immediately, if you see that, right, if the average density of 5.5, the average density, also known as the bulk density, you'll sometimes hear that reference. If it's 5.5, that means, the Earth is made of, lots of rocks that have a density of 3, and then of course there's a good deal of iron and nickel, which has a density closer to 8. And so, this is kind of like the average density of the Earth, or, that's what that means. That's what so there's things in the Earth, of course, that are much less dense, like water and ordinary rock. And there's stuff that makes up the Earth that is much, much more dense, like iron and nickel, and even, although there's not that much, not comparatively that much of it, but things like uranium. Uranium is extremely dense. But, I almost hesitate to mention uranium because there's not that much of it compared to the entire mass of the Earth. All right, so now what more can we figure out about the interior of the Earth? All right, so that's kind of a story unto itself. So what we use to figure out what's going on in the Earth now yeah. So here, let's go back to this picture back here. So it's roughly 6,400 kilometers to get to the center of the Earth. The human race has, dug down. So about, by the way, in miles, that's about 4,000, roughly 4,000 miles. The human race has dug down into the Earth about a little more than 7 miles. So we're nowhere close to digging to the center of the Earth. So that's something to keep in mind. So how do we know? I mean, we're about to talk about, what the center of the Earth is made of. And the reason that we understand what's going on with the center of the Earth is sound, seismic waves. The waves can pass through certain material and not pass through other material, different waves I'm talking about. All right, I'll talk more about this in the next video.